Okay, so let's take a look at the 3 chapters that make up Unit 4. So Chapter 10 was about severe weather, and we started out talking about just regular air mass thunderstorms. They are relatively simple, kind of short-lived, and they go through these 3 stages, cumulus, mature, and dissipating. So with regard to those 3 stages, you're going to want to generally know that the cumulus stage has an updraft, the mature stage has an updraft and a downdraft, and that's when you get your severe weather. And the dissipating stage has only a downdraft. So those are the 3 stages of a simple air mass thunderstorm. Those are also the 3 stages of a thunderstorm cell that's a supercell, or these different thunderstorm cells that might be part of a squall line or mesoscale convective complex. With regard to entrainment, that's basically dry air that's moving its way from the edges of a cumulonimbus cloud into the cloud, and it causes an assortment of water droplets. But remember that CB is actually the cloud type cumulonimbus cloud, so that goes back to what we learned earlier in the class. Wind shear, by definition, is basically wind that's changing either speed as you go up in elevation, or change elevation, or it's changing direction. So we said that wind shear actually is what gives us these tilted cumulonimbus clouds, and the tilted cumulonimbus clouds actually can be more severe than the majestic ones because they're they can actually have rotation in there that can give you the mesoscale convective complex, that gives you the mesocyclone, that rotation to give you a tornado. But the other thing is that their updrafts and downdrafts don't snuff out each other. So tilted cumulonimbus clouds from wind shear are a deal usually. Thunderstorm cell. So I brought in this figure. So the next few terms under thunderstorm, under supercell thunderstorm, you need to generally know. But in a supercell thunderstorm, what happens is the updraft and the downdraft are wrapped around one another. So on this figure, kind of recognize we have the red is the updraft, the blue is the downdraft. Also notice the overshooting tops, kind of that crispy thing that's on top of the anvil. And the gust front is associated with the downdraft, kind of shown here in I guess blue, kind of, the gust front. So know that. Microbursts, what they are basically kind of this straight vertical wind that is associated with the downdraft. And remember, the downdraft actually is created from the precipitation. Squall lines and mesoscale convective complexes go together. They are both types of multi-thunderstorm cells. And in the squall line, you have frontal lifting from a cold front or dry line. And in mesoscale convective complex, you basically have those thunderstorm cells that are kind of blobby. And the mesoscale convective complexes basically need a big chunk of moist air that's unstable. And you kind of have the many thunderstorms spawn within it. 2 types of lightning. So there's the cloud-to-cloud lightning, and actually that is 80% of all lightning, and that's the part that's not necessarily going to get you. Another name for cloud-to-cloud lightning is sheet lightning. And then there's the cloud-to-ground lightning, and that only makes up about 20% of lightning. Of course, that's the one that will get us, right? The next thing, just basically, and it's a multiple choice question, know that if you see words like leader, flash, and that should be stroke, not stroke, that actually they are all associated with lightning. And you may have learned this old adage growing up. If you, of course, there's oftentimes a delay from when you see the lightning to when you hear the thunder. And if you count that delay between the lightning and the thunder, and if you divide by 5, that's actually the number of miles away, approximately, that lightning is. So if it was like 10 seconds between seeing the bolt of lightning and hearing the thunder, that would be 10 divided by 5, or 2 miles away. The enhanced Fujita scale is the scale we use to categorize tornadoes, and it is a scale from 0 to 5. And notice one of the things about categorizing tornadoes is that it's done after the fact. So a wall cloud may or may not precede the tornado. But what wall clouds do is they drop down from the base of the cumulonimbus cloud And like I said, they may or may not be the precursors of a tornado. So speaking of tornadoes, a funnel cloud is basically a tornado that does not extends from the cloud, but it does not reach the ground. The next one, tornado watch or tornado warning, or sorry, tornado alley. Tornado alley is basically a region in North America that's prone to tornadoes. Tornado watch. The watches are actually issued by the Storm Prediction Center in Norman, Oklahoma, and they mean the watches because atmospheric conditions are favorable. Compare that to a warning. Of course, a warning means that a tornado has been spotted, and those are issued more locally by the National Weather Service. So on to Chapter 11. And in Chapter 11, of course, we kind of switched gears from the wind-based to the maritime. So hurricane, typhoon, and cyclone, those are all names for what we call tropical cyclone. So in North America, we call them hurricanes. In Japan, they call tropical cyclones typhoons. And in Australia, they would call tropical cyclones cyclones. The next two things are kind of self-explanatory. The deadliest hurricane was the Galveston, Texas hurricane back in 1900. The most costliest hurricane to date has been Hurricane Katrina for North America. The eye of the hurricane has got a central low pressure at the surface anyway, and it's generally calm. That would get you where you need to go for the test. Conditions required for a hurricane, there are generally 3 conditions required for a hurricane. You need to have nice warm water. You need to have the spin from the Coriolis force. And one of the things about getting the spin is we said, when we talked earlier in this course, you get spin. If you're too close to the equator, you have no spin. So that's why, even though it's nice and warm at the equator, you need to go at least 5 degrees, either north or south of the equator, to get the spin that you need. The third ingredient for hurricanes would be that nice unstable atmosphere. Naming hurricanes. All right, so I kind of jotted down, I think I got most of them. One of the things is that the hurricanes are named once they become a tropical storm. We'll talk about that's a stage of a tropical cyclone. We alternate male and female names to name our hurricanes. We skip letters like Q, U, Z, and X and Y. Each basin actually has its own set of names. And the names actually will repeat themselves. The lists will repeat themselves. Names, though, can be retired from those lists. And last but not least, if we run out of named letters in the alphabet, in our basin anyway, we move on to the Greek alphabet. Greek letters, I guess I should say, not Greek alphabet. Then on to the stages of a hurricane or tropical cyclone. These first 2 stages actually aren't real stages, I suppose. Westerly waves that kind of for us start off the west coast of South America. Then tropical disturbance. Tropical depression, tropical storm, and tropical cyclone are full-fledged. Those are what you'll see on your test. So depression, storm, and cyclone. And in each of these cases, the winds are increasing and the central pressure, low pressure, is getting lower. So the Saffir-Simpson scale is used to categorize hurricanes or categorize tropical cyclones. And notice that these are categorized during the event as contrasted to tornadoes. And the scale, the hurricane scale, goes from 1 through 5 instead of 0 through 5. So actually the next one, I simply say, what are the differences between categorizing tornadoes and hurricanes? They use different scales, and actually one's 0 to 5 and one's 1 to 5, and one's actually done after the event, tornadoes, and one's during the event, like hurricanes. So the last one is destructive forces of hurricanes. So storm surge actually could have been its own term on this review sheet. So you should kind of know what storm surge is. It's that wall of water that is associated with the eye hitting landfall. And flooding is associated with either storm surge and or the spiral rain bands. And then tornadoes actually, or winds, are associated with the tight isobars around that central low pressure, that steep pressure gradient. Tornadoes are actually come from the thunderstorms that are embedded in both the spiral arms and the eye wall. So all sorts of things to get you in a hurricane. So on to the last chapter in this unit, forecasting. So the first three terms basically know the acronyms here. So NOAA stands for National Oceanic and Atmospheric Administration. National Weather Service are more local, and they're abbreviated NWS. And we've come kind of full circle. We talked about these ASOSs earlier on in this class. And remember, this is basically kind of this set of equipment that automatically measures atmospheric conditions and automatically sends that information to folks who need it, including airports. So ASOS stands for Automated Surface Observing System. And then I think on the test I basically say something about these weather balloons are sent up twice a day from locations all around the world, and they're sent up at the same time. I just think that is so cool. Geostationary satellites, I went ahead and brought in a figure. So geostationary satellites are the ones that are kind of farther than the polar orbits, and they generally kind of keep up with the Earth's rotation. They hover over one location, so as the Earth spins, that's in sync. Their orbit is in sync with that Earth rotating. The next one, with regard to the three types of images in general that the satellites can send us. Visible images from satellites, remember, they can only be taken on the day side of the Earth. Infrared actually is getting a heat signature from the Earth. And water vapor images can be used to help predict where there will be fog, where we're more likely to have cloud formation and precipitation. Numerical weather forecasting is generally where you use computers and you have models or programs in these computers, and the models or programs are supposed to kind of mimic what Mother Nature does, and then you feed the computer these current conditions, generally called initial conditions. So that's the numerical forecasting method. Analog method or analog approach. Basically what you do is you find a day in the past that is just like today. And then whatever in the past the next day's weather was, that's what you forecast tomorrow's weather to be like. So find past day just like today. Weather after that day is what our tomorrow's forecast will be. Hope that makes sense. Analog method. Persistence forecasting is basically tomorrow's weather is going to be what today's weather is. Okay, so basically the weather is just going to persist. Trend forecasting kind of uses, I used the example in class where we usually look on a map to kind of our west to see what the weather's going to be like tomorrow, and that's a type of trend forecasting because we are here under the influence of the mid-latitude westerlies. So you basically look upstream, okay, to basically anticipate what our forecast is going to be. Nowcasting is similar to trend forecasting, but it's just on a shorter time frame. The next one, butterfly effect and chaos. Actually, they can kind of be summarized in that a small change or a small difference in kind of what we see our initial, we feed our computer initial conditions, a difference in those initial conditions, a small difference, can make a dramatic difference in what the forecast from that numerical forecasting will be. That's called the butterfly effect or chaos in general. So related to the butterfly effect and chaos in weather forecasting is this ensemble forecasting approach, where you recognize that small differences in your initial conditions could have drastic effect on your forecast. So basically you go with that, and so you run a set of forecasts, all for the same period of time with slightly different initial conditions. And then what you do is you look for a pattern. And so, like, if you keep seeing a particular forecast show up, that's the forecast that you go with. So look for a pattern and select the most likely forecast from something that reoccurs. And then the last one, there are 3 reasons in general, probably more than that, but why our forecasts go wrong. Okay, one is that that butterfly effect or chaos, and kind of there's a little bit of play in all of those initial conditions that are fed to your computers, and so with that play, that uncertainty, you're bound to kind of have a big question mark with the forecast. The next one is there are holes in the data, and the example I used, for instance, when we try to get initial conditions over the ocean areas, we don't have all those different, we don't have ASOSs, right, to send up that information. So we definitely have holes. And then the last one is that as much as we try to program our come up with programs to feed our computers that actually mimic Mother Nature, good luck. That's harder to do. We can't mimic Mother Nature even though we try. So I see now that I have forgotten my 2 code words. So I'm going to just go ahead and give you the code words up here in the upper right hand corner. So let's go with the first code word is summer. Summer. So there's 2 of them. Okay, that's the first code word. And the second code word is Draco. Draco. D-R-A-C-O. Okay, Summer and Draco. You let me know that you watched the video by giving me those two words.